So there was a question about modeling how things change, and we were doing that with sequences. And specifically, the question was related to our last exam, where we had a problem related to a loan. So I just wanted to review some basic concepts of how things change. So we can imagine, for example, that I've got a quantity and I'm going to pretend it's like a bucket, and there are things that go in and there are things that go out. And so my new value is always going to be equal to what I had before. We're going to subtract what leaves, and we're going to add what joins. So this is really closely related to what we did very early in this semester, where we had rates of change. So if I were to look at this, the change, which is equal to what I had for my new value minus my old value, my change, the new value minus the old value, is going to be equal to adding what joins and subtracting what leaves. So we had two related concepts. In chapter 1, we had something called a rate of change. And so, for example, if I was measuring the volume of water in this container and I had a rate, so this is a rate of how fast water is coming in, and I have another rate of how fast the water is going out, then my volume is changing in time. And so I can think about the rate of change of my volume. So this is the rate of change of the volumes. It's the rate that it joins. Sorry, that's coming in. Where did I put my eraser? We add the rate that comes in, we subtract the rate that goes out. So this is a rate. If I wanted to find out how much of a change and this was on one of our early exams, I think both exam 1 and exam 2, the change in the volume, the new minus the old, is equal to the rate times how long you spent. And we were reinforcing that at the end of the semester as we did the definite integral. So this is going to be equal to my rate of change times how long I spent. Okay? So that's just a quick summary of what we did very early in the semester. And we're going to be using those concepts to generalize for sequences. So now let's imagine that instead of water, I have something related to money. And for example, if I have a loan, the reason my loan gets bigger is the bank charges me interest. And the reason that my loan gets smaller is I make payments. So you have to realize that this is what you owe. It's not how much you have. So if I have a loan, let's call L of t, or let's do n. L of n is my loan balance after n payments. Then I can think of my new value, this is my new value, is going to be my old value plus the things that make it bigger. So this is what makes it bigger. Input's not the right word. Well, here it gets bigger because I charge interest, and it gets smaller because I make payments. Okay. Now my interest is usually a percentage rate, and the way that I do that is I do a percent times my balance. So now we need to think about a specific example. So suppose I have a loan that charges 6% interest annually. That means that 6 over 12 is 0.5% monthly. So you have to pay attention to how a question is posed, whether it gives it in terms of annually, which is for every 12 months, or monthly, which is every month. And so the interest, remember, a percentage is out of 100, so it's 0.5 out of 100, which is 0.005, times my loan balance. That's how much interest is going to be. So my equation will be my old balance plus my new money I owe because of interest, which is the percentage rate times my loan balance. And then we'll subtract however much my payment is. So let's do a little more clear. Let's pretend that my monthly payment is $100. Well, that means every month I subtract $100 from my loan. These two terms are the same type. It's a number times ln. So my new balance is ln factors out 1 plus 0.005 times ln minus 100. This is the recursive equation. And then my initial balance is how I start my equation. I've got an initial value, I've got my monthly balance. Let's pretend for just a minute that my original balance is $2,000. So let's do a loan for $2,000. I would then be able to find my sequence, and this is recursive, so to get my next balance, L1, this would be 1.005 times 2,000 minus 100. That gives me 2010 minus 100, so that's $1,910. That would be my balance after one more month. So when I have a recursive model where I have a projection function, so here's my input, my old balance is the input, my new balance is the output. That means my projection function takes my input, multiplies it by 1.005, and subtracts 100. I can find a fixed point. And that's what would lead to an equilibrium solution. I would solve the fixed point equation where x equals 1.005x minus 100. What we're doing is we are taking both of my loan values, my new balance and my old balance, at equilibrium, they're the same thing. And so now I'm going to solve. I'll subtract 1.005x from both sides. And then I can divide by negative 0.005. And x is equal to, let's see what that is, 100 divided by 0.05. That's 20,000. What that means is if I started with a loan of $20,000 and I was charged 6% interest a year, and I only paid $100, my balance would stay that forever. This is my fixed point. One of the things we did with projection functions, when it was a form, see, this is a linear projection function. It's a slope times the input plus a number. My sequence has a explicit formula where I've got my fixed point plus some constant that we need to find times my slope raised to the power n. And our fixed point is 20,000. And in order to find this value of a, we're going to use our initial condition, which is when n equals 0, ln is 2,000. So 2,000 is 20,000 plus a times 1.005 to the 0, which is 1. And so a is going to be 2,000 minus 20,000. a is negative 18,000. And I can write down my formula. It's the fixed point minus the a, 18,000, times 1.005 to the nth power. And now I can use that fixed point, or sorry, I can use that explicit formula to solve other questions that I might have. For example, when my loan balance will be paid off.